Okay, so we had previously discussed the theory of rotational equilibrium where the sum of the torques was zero. Here we're going to look at rotational dynamics where there is a net torque. There is an unbalanced or resultant or net torque. And we showed in the lab previously that that net or unbalanced torque was directly proportional to the angular acceleration. So if we plotted a graph of the net or unbalanced torque versus angular acceleration, we got a straight line. Now, what does that graph tell us? Well, if we harken back to Physics 11, you may recall an experiment where you varied the net force on a system, and then you found that that varying net force produced a varying acceleration in direct proportion. Then you took the slope of that graph and you said it has units of kilograms. Why? It's just the mass of the system. Well, in a similar manner, the slope of this graph ends up being related to, well, it's not going to be the mass, but it's going to be the inertia. It's the rotational inertia, or as it's sometimes called, the moment of inertia. Now, what does that measure? Well, we'll talk about that in a second, but let's just write an equation then for this graph. Rotational inertia, we give the symbol I, and so just as this graph has an equation, F net is ma, this graph has an equation, net torque equals I times alpha. Remember, y equals mx plus b for a straight line. B is 0 for this line. The slope is the inertia I. The x-axis is alpha, and the y-axis is net torque. So this is Newton's second law for rotation. It's the rotational equivalent of F equals ma. Now, with the linear dynamics, it's pretty clear what the mass m is. It's the total mass of the system that we can measure by finding the weight on a balance. What does the rotational inertia I represent? Well, inertia means resistance to change. So if you've got a large rotational inertia, or a large moment of inertia it's called, that's going to be something that's relatively hard to rotate. There'll be lots of resistance to rotation. An object with a small moment of inertia is something that spins easily. There is less resistance to rotation. Now, what are the units of that? Well, as the slope of the torque versus angular acceleration graph, it'll just be the ratio of torque units, which is Newton meters, over angular acceleration units, which is rads per second squared. Now, a rad is just a placeholder, so meters over rads is just meters. So this becomes Newton meter second squared. A Newton, however, as a force, is a mass times an acceleration. So that's a Newton. And then we're going to multiply that. I'll just show the substitution here. So this part here is Newton. And it remains to multiply that by meters second squared. Clearly, the second squared part cancels, and we find the units for moment of inertia or rotational inertia are kilograms times meters squared, which suggests that a rotational inertia is a mass times a distance squared. Which mass? Well, it's the mass of the rotating object. Which distance? Well, presumably, thinking back to torque, it's the distance the mass lies from the rotational axis or the pivot point. Now, we're going to see later that the inertia does depend on the shape of this object. For now, we're just going to deal with point masses. That's like this one. It has no shape. All of its mass we can pretend is concentrated at a point. So the inertia of a point mass is a mass times the distance squared. The distance is how far is the mass from the fulcrum, the pivot point, or the axis of rotation. So here's a demonstration we'll look at in class. Here's our first example. Here we have a skater. They have a certain amount of inertia, and somebody, maybe your skating coach, is pushing on them, exerting a force on their outstretched hand. Now, they've set pick down here so that they can rotate, and the rotational axis goes through the top of their head, and that force is acting a distance r, which is the length of their arms away from that axis of rotation. So we want to now find the speed at which the skater spins after they're pushed for 0.2 seconds. So we can find the torque here, because a torque is a force times a distance. So we're exerting 10 newtons of force, and that force is acting 75 centimeters away. So that's 7.5 newton meters of torque. The inertia is just given. You see, the skater, because they have mass a distance away from the rotational axis, even in their head, right? There's some mass of the head that's not right at the rotational axis. And so this is just given. It's 1.75 kilogram meters squared of rotational inertia. So we can find the angular acceleration. We know that Newton's second law says torque is I alpha, F is ma. So alpha is the ratio of the unbalanced torque to the inertia, 7.5 newton meters over 1.75 kilogram meters squared. So 7.5 over 1.75, that's 4.28 rads per second squared. Now, we are told that the skater's at rest, and we want to find the final speed after 0.2 seconds. Well, now we get back into our kinematics. We know the initial speed, acceleration, and time, so we'll use this kinematical equation in order to find the final speed. Vf is Vi plus At. It was 0.2 seconds, so one of the seconds cancels. We end up with rad per second units. And then that should be 8.56, so it's going to be 0.856 or 0.86 rads per second of final speed. Now, we're now going to imagine that the same skater now has 3 kilogram masses in their hands. Say they're doing this for some exercise. And the skating coach is going to push with the same force exactly the same distance away for the same amount of time, and we want to find the final speed that the skater reaches at the end of that push. So I'm going to ask you to follow the previous solution because there will be some quantities that are the same. There is much that is the same. So follow through that same previous solution and try and solve this on your own. You could pause the video at this point, try it on your own, and then compare with my solution. Okay, so you had a crack at that. Hopefully you realize that the torque is the same because the force and distance are the same. So it's the same 7.5 newton meters of torque as in the previous part, part A. The inertia is what is changing here because the inertia is going to be the inertia of the skater, which hasn't changed, plus the inertia of the two masses that the skater is holding, the two weights. Now, we'll treat these as point masses, and therefore the inertia, I'll put this in here, 2 times the inertia of the masses. And I should really call it just 2 times the inertia of a single mass to be most precise. So the inertia of one of these masses is going to be its mass times how far away it is from the rotational axis squared. So they are 3 kilogram masses, and because they are held in the hands we know are 75 centimeters away, the arm length given from the rotational axis. And then it's the same skater, so what was it? It was 1.75 for the skater's body. So we add the inertia of the skater's body to the inertia of the point masses to get the total rotational inertia of the system. So there's the rotational mass of the masses, and then we add the 1.75, and we get 2.66 kilogram meters squared. Okay, I'm not sure what happened there, but I just did it again, and I think this answer is better, 5.125. So now we can repeat the process, find the acceleration, just as the ratio of torque to inertia, and then find the final speed using kinematics. And the final result ends up at So the final speed ends up at 0.29 rads per second, which is slower than the previous example. And it's slower because we have more inertia now. So that same force will not create the same final spin speed. Okay, what follows there is a few demonstrations that we'll do in class related to angular dynamics. Next, we want to get into the idea mentioned previously, which is that the shape of the object actually affects the amount of inertia. We know that for point masses, the inertia is just mr squared, but if we deal with other geometries, we'll find we get different inertias. So for a point mass, it's mr squared. So let's consider some other geometries. And in these geometries, the mass will be distributed over certain volumes of space. Now, really what we need to do in those cases is we need to break the object up into tiny little bits of mass, and then let's call it little mass mi, and then include how far it is from the axis of rotation, and then add up those little bits of inertia. Well, the first shape we'll consider will be a hoop. Now for a hoop, all the little bits of mass are the same distance r from the rotational axis, which is assumed to be the center. So because r is the same for all of them, we can pull it out of the sum just by factorization. And we end up summing up the little bits of mass. Well, summing up the little bits of mass gives us the total mass. So that we find for a hoop, because all the mass is the same distance away from the center, hoop inertia ends up being just the same as point mass inertia, although m and r mean different things. Now m means the total mass of the hoop and r means the radius of the hoop, whereas before it was the mass and the distance from the rotational axis when we were talking about a point mass. So same result, slightly different meaning. Let's next go to another geometry. Let's go to the geometry of a solid disk. Now with the disk, because some of the matter will be in closer to the center, it's not all on the rim. Because of that, we expect that the inertia is going to be less than mr squared. So we've got to add up our little bits of mass times the distance that it is away from the center, which is given as the axis of rotation. Now, this ends up being a really nice calculus 2 problem. We actually break the disk up into a series of hoops, and then we add up hoop inertias from tiny hoops here at the center to a big hoop of radius r at the edge. And when you do that, I won't do it here, just because a number of people haven't done integral calculus yet, you actually end up with a factor of a half, so that a disk inertia is 1/2 mr squared. That compares with hoop inertia, mr squared. So those are two geometries for which we can calculate the inertia. There'll be a little demonstration here. It's called a moment of inertia race, disk versus hoop in class. Here's a problem. Now this is a nice summative problem because it includes dynamics and kinematics. So I'll ask you to read through, give this one a try. After you've tried it, turn the video back on and play through my solution. What we're looking at here is like a disk in top view. Maybe, I don't know, something like a curling rock, and we're holding it at the center and applying a force on the edge to spin it. Or it could be something like a record player, and it's on the record player, and we're just applying a force to make it spin. So give this problem a try, then play the solution. All right, so here's the solution. So viewed from above, we see that there's a torque on this disk. The torque is going to be the product of the force and the distance away, which is the radius of the disk. Now, the inertia of the disk, let's start with that. Because it's a disk, we know that disk inertia is 1/2 mr squared. We didn't do the calculus derivation, we just stated the result. So the mass is 5 kilos and the radius is 0.4 meters all squared. The torque is a force times a distance, and we applied a force of 15 newtons, and that acts 0.4 meters away from the axis of rotation, so that's the amount of torque. We can then find the acceleration. Torque is I alpha, implies the acceleration is the torque over the inertia. And we're asked to find, let's see, the time to reach 12 rads per second of final speed. Waiting. Oh, there it goes way down there. Okay, so time, and we'll do that using kinematics. To time to reach 12 rads per second from rest will be given by this expression here. Now, you should be able to show that your acceleration works out to be 15 rads per second squared, and therefore that your time is 0.8 seconds. That's the final answer here. So that's a fairly straightforward problem in angular dynamics. You see there's quite a few straightforward steps all put together to get the final result. Let's try and look at a couple of other geometries now. First of all, let's consider rod geometry, so long thin things. Well, it turns out that the inertia of a rod depends on where the pivot point is. For the pivot at the end, the inertia is 1/3 rod mass times rod length squared, the total length of the rod. For a rod pivoted about the middle, the inertia is 1/12 ml squared. Now, all of these results are provided on your formula sheet, but as always with physics, it's helpful and beneficial to memorize these results. Another final geometry of interest is a ball, a sphere, and the inertia of a sphere is 2/5 mr squared for a rotational axis that goes through the middle of the sphere. Okay, so an example then. Once again, try this one. Pause the video, try it, and then play my solution to see how you did. Okay, so from the given information, we can find, first of all, the angular acceleration, because we know that it starts at rest and it speeds up to 25 in 0.75 seconds. So that gives us 33.3 rads per second squared of angular acceleration. We're given the amount of torque in the wrists, and therefore we can find the amount of inertia, just dividing the torque by the angular acceleration. That works out to 0.3 kilogram meters squared of inertia. We will treat the sword as a rod pivoted about the end, for which the inertia is 1/3 ml squared. So putting in 0.3 and putting in the given length, which is 0.55, we can solve for the mass of the sword. Finally, for the speed of the tip, when it's rotating at speed omega, we remember that the speed of the tip depends on the distance that we are from the axis of rotation, which is the length of the sword. So the length of the sword is 0.55 meters, and at the end we're spinning at 25 rads per second, so we can find the speed of the sword tip. Okay, so those values work out to be almost 3 kilograms for the sword, and then the speed of the tip is going at 13.75 meters per second. A final idea then, having introduced Newton's second law for rotation, torque equals net torque equals I alpha, and then having the various inertias, mr squared for a point mass, and then different inertias for the hoop, the disc, rod middle, rod end, and sphere. A final idea is, you see, each of those inertias depends on where the pivot point is. So for the disc, we found the inertia when it was pivoted about its center. What if the pivot point is not at the middle? Well, it turns out that if you have, say, an off-center disc, an eccentric disc, you can find the inertia about that new pivot point using something known as the parallel axis theorem, which states very simply that the inertia about some new pivot point is the inertia when the object is pivoted about the center of mass, plus the mass of the object times how far you've moved that pivot from the center to the new pivot point squared. That's known as the parallel axis theorem. Let's apply it, first of all, to a case where we know the answer. Because we know the inertia of the rod about the end, but the parallel axis theorem says that the inertia about the end should be the inertia about the center plus the mass of the rod times the distance that we're shifting the pivot squared. Now, how far are we shifting it? Well, if we're starting at the middle and shifting it to the end, that distance should be L over 2. Now, the inertia of a rod pivoted about its center, we said earlier, was 1/12 ml squared. So if you add a 12th, and L over 2 squared gives you a quarter, a 12th plus a quarter is a third, because that's 1/12 plus 3/12 is 4/12, which is 1/3. The lost art of fractions, which is the value that we gave earlier. So this is consistent with what we would expect. Now let's use the parallel axis theorem to do something where we don't know the answer in advance. Let's find the inertia of a disk pivoted about its edge. Well, according to the parallel axis theorem, the inertia of the disk pivoted about its edge, that's an eccentric disk motion, is the inertia of the disk pivoted about its center of mass plus a term, mass of the disk, times the shift distance squared. So here we're shifting the pivot point from the center out to the edge. That's a distance r. So the inertia is going to increase by mr squared as compared with when it was pivoted about the center. Now, the inertia of a disk pivoted about the center was given as 1/2 mr squared earlier. Half mr squared plus mr squared is 3/2 mr squared. So if we had an angular dynamics problem where we had a disk pivoted about its edge, this is the inertia that we would use. So that concludes our presentation on angular dynamics. That's the parallel axis theorem. In class, we'll do some demonstrations and more practice problems to become masters of torque equals I alpha.